All right, let's go ahead and start talking about the last part of this series, and we will start with Kirchhoff's laws, or rules, sorry. Now, I'm going to touch on this very briefly, and you won't be using this to calculate like it is in your book, but I just kind of want to get you guys the information. So he has two rules, and the first one is the junction rule, which states that the sum of all currents entering a junction must equal the sum of currents leaving the junction. So whatever comes in must also go out, okay? And this is due to the conservation of charge. Remember that currents are the flow of charge, okay? So if we have a flow of charge going into something, then we must have the same flowing out, okay? So in this diagram here, get another pen. In this diagram here, you see I1 is traveling towards junction A. So this is what a junction would look like. You can also call it like an intersection. You can think of it that way. And so this current will flow towards that junction and then split up into two separate currents. Okay, so you have current I2 and I3. So I1, or that overall current, should equal I2 plus I3. Okay, this is something that we saw before when we were looking at circuits in parallel. Okay, so this is the same exact idea, just with specific rules written. Okay, then we have the loop rule, which is the sum of changes in potential around any closed circuit path or loop must be 0. So the overall voltage changes throughout the circuit should sum to equal 0. Another way we can say that, and this we saw in series. We were looking at series circuits. The overall voltage, the total, is equal to V1 plus V2 plus so forth. It's the same exact thing, just saying 0 is equal to the total voltage, or whatever is being applied, minus V1, minus V2, minus ... however many there is. Okay, so these are just restatements, I would say, of what we have already looked at. Okay, and with that, I wanted to just show you this diagram. This is actually from a different textbook, but the one in your guys' textbook was kind of confusing a little bit, in my opinion at least. So this is a diagram showing you the voltage difference, the potential difference, I should say, what that sign would look like, so positive or negative, when we have a current and direction of travel that are either in the same direction or in opposite directions, okay? So in the same direction, I'll put same direction on this side, we have a direction of travel of, say, electrons traveling in this positive x direction. The current is also traveling in the same direction, positive x, say. We will have a voltage drop, so a negative IR, okay? Same thing here. We have direction of travel, positive x direction, and our current would be flowing from the negative to the positive here, and so we'd have a positive voltage. When we have a opposite direction of travel, we will have the exact opposite. So in this case, we have direction of travel being in the negative x direction, but the current traveling in the positive x direction. We will have a difference in voltage of positive IR. Okay, so I just kind of wanted to introduce this idea, but this is like supporting the stuff that we have already talked about, but I just wanted to throw it out there for you guys in case you were interested. Feel free to look at the textbook for some more information if you want to, but it's not necessary for the purposes of this course at least. Okay. So the last thing I want to talk about, and I keep saying on the end of my other slides that we will talk about this, but now's the time. Talking about capacitors in series and in parallel. So this first case, we are going to look at capacitors in series. And this is going to look different than our resistors in series. Okay. So, capacitors in series, we need to recall that capacitance, remember C is capacitance, is equal to charge divided by voltage. Okay. And in series for capacitors, I should say, the voltage, the total voltage, let's say total, is equal to all of the individual voltages across each of the capacitors added up. So voltage at C1, say. Okay, say C1 is right here. We would have some V1, V2, and V3. Okay, so the voltages are different. Okay, the charge remains constant, of course, and that is due to the conservation of charge. Okay, so Q will be the same throughout, if you see it in this diagram. And we will have different voltages. So this gives us, through a little bit of calculation, not a ton, that 1 over our capacitance in series is equal to 1 over C1 plus 1 over C2 plus ... Okay? So this looks very much like the resistors in parallel. So we can compare to resistors in parallel. Okay, so this might seem a little bit confusing, but this is due to the equation here. Okay, this is due to the charge dependence of capacitors as well. Okay, so you can see in these two diagrams, we have our capacitors in parallel. And remember, capacitors store charge. And we have our voltage that's hooked up, our battery. And in the second bit, that would be breaking that down into the capacitance in series. Okay. All right, now let's look at this in parallel. Capacitors in parallel have the same charge. They would have as if they were connected individually to the voltage source. Okay, so this is going to be similar to the resistors when we're looking at voltage, or actually, yeah, voltage in parallel. Yes, okay. So, and you can look at that as well in the other video or in the PowerPoint. Remind ourselves. So, Q, our overall charge, will equal each individual Q across the different capacitors. Okay, so for C1, you have a charge Q1. For C2, you have a charge Q2, and for C3, charge Q3. Okay, the voltage now will remain the same in parallel. Okay, and due to these two things and the equation that we were just looking at for capacitance is equal to Q over V, we find that the capacitance in parallel is equal to C1 plus C2 plus ... Okay, so again, this might be a little bit tricky to get used to because it's kind of opposite to the resistors that we were looking at before, okay? But hopefully this makes sense for us, okay? All right, and then here is a combining capacitors in series and parallel. Again, it'll be very similar to what we were doing with resistors, but now with the rules of capacitors. Okay, so here we have, let's see, these two guys in series, now these two guys in parallel, and then you can get your total. Okay, so this may seem a little confusing, but it's going to be a very similar process, just the equations are different. Okay. All right, the last thing I want to talk about or touch on is the idea of a voltmeter and an ammeter. And hopefully we'll be able to do this in class, but I'm not positive. Sorry, that's my dog. A voltmeter measures voltage, surprise, surprise, and is placed in parallel when you want to measure something. So if I'm looking at this schematic here, and I want to know the voltage across this resistor here, R sub L, I will place it here and here, and that will be in parallel with the circuit, okay? That'll be in parallel with this resistor, I should say, okay? The ammeter will measure current, okay? And with that, you want to place it in series to measure. So you insert it as so that the current will just flow right on through it. Okay. Now, hopefully, again, we can see this in lab, but let me see if I still have, there was a, oh, what the heck? There we go. Okay. There was a really cool FET simulation. I think it was this one. And we can do it on here through a simulation. Yeah, perfect. So this one is kind of fun because you can kind of build your own thing, which I think is pretty cool. So if I want to create a little circuit, take a battery, plug it into a wire, I'm going to put it into a light bulb here. So I'll just connect that wire. What else do I want to put in this guy? You can choose all kinds of different things. We've got battery, light bulb, resistor, a switch, which would be cool, a fuse, what else is different? A paper clip, which, I mean, I don't know how useful that'll be. A dog, which, again, don't think so, but it's a way for us to kind of experiment. And maybe I can make a lab out of this. I think that would be pretty interesting. But in any case, let's go ahead and do a switch. That would be good, I think. So let me kind of move this stuff around. Okay, well, you get the point. It's a funny shape, but you get the point. We've got a light bulb connected to a battery, connected to a switch, and back to the light bulb. And if we want to measure something, we'll take one of these voltmeters and put it on one side of either side of this. I'm trying to show this so it makes more sense. Either side here. Hopefully you can see that it's on either side of the light bulb. And then we can close the switch and we will get the voltage. So this is exactly what we could do, but in lab, and it would be a lot of like plugging things in, plugging in wires. Stop the switch or turn off the switch. I can pull that away and then take my ammeter. And again, this will be placed in series. Okay, so you'll just plug that guy right in and then close the switch, and you now have the current of this system. Okay, So this is something that you can play around with. This is in section 21.4, and it might help with your understanding of actually a lot of these concepts. And you can, let's see, combine lots of different things here. What is advanced? Oh no. Combine a lot of different things, so add more batteries. You can change the voltage of the one battery you have and kind of see how things change when you start to do series, parallel, and a combination of all of those. Okay, so if you guys have questions about anything, let me know. And yeah, we'll get some practice with this next week, and we'll see you then. Thanks.